This is the second video in the series on the concepts of probability for machine learning. Let's start with a quick recap of the previous video. When we calculate the average outcome of an experiment by summing all observed outcomes and dividing by the total number of observations, we are, in effect, using our approximate estimate of the underlying probability distribution of the experiment. A probability distribution assigns a numerical value to each possible outcome so that they all sum up to 1. We can improve our estimate of both the average outcome and the probability distribution if we increase the number of observations. From a machine learning standpoint, this means increasing training data improves model predictions. In this video, we will examine how the concept of average has a connection to another concept that we use extensively in machine learning, entropy. Entropy quantifies the information content in an event. That is, entropy assigns a numerical value for the information content in an event. For example, consider the probability distribution made up of two events: sun will rise tomorrow with probability 0.9, and sun will not rise tomorrow with probability 0.1. The information content in the event sun will rise tomorrow is very low because we already know it will. On the other hand, if someone told us sun will not rise tomorrow, that would surprise us, even if we may not believe it. Entropy essentially captures this intuition. High probability events have low surprise value. Low probability events have high surprise value. Entropy quantifies the level of surprise associated with an event by taking the logarithm of its probability. Since the logarithm of fractional probabilities is negative, we negate it to obtain a positive value. Therefore, the entropy of an event is the negative logarithm of its probability. Now, to find the entropy of a distribution, we do exactly what we did for finding the average value of observations. We weight the entropy of each event by its probability. It is worth noting the difference between the entropy of an event and the entropy of a probability distribution. The entropy of an event is the information content of an individual event. The entropy of a probability distribution, on the other hand, is the average information content across the entire distribution. We will now see how the entropy concept is used to train a model. Let's say we want to train a model to classify an input image as a cat or a dog. Training a model, as we saw in a previous video, what is a machine learning model, is essentially making a model learn from its errors. The error in prediction is captured by a loss function, which quantifies how far off is the model prediction from the true value. So let's say the model predicts a probability distribution for an image, 0.8 for dog and 0.2 for cat. Let's call this the predicted distribution. Let's say the probability distribution humans assigned for the same image is 0.9 for dog and 0.1 for cat. Let's call this the true distribution. When we compute the entropy of the true distribution, the numerical value of the computation is lowest only if the probability values used to calculate the entropy of individual events precisely match the true probabilities of those events. If we use different probability values to calculate the entropy of individual events, it would lead to a higher entropy value for the distribution. We can leverage this insight and use entropy as a loss function. In the example case mentioned above, if we substitute 0.8 and 0.2 as the probability values for the events when calculating average entropy, the resulting value would be larger than if we used 0.9 and 0.1 instead. In general, if the predicted probability distribution differs from the true distribution, the calculated entropy, when weighted by the true distribution, will be higher. Weighting the entropy of the predicted events with the true probability distribution is commonly called as cross-entropy. Driven by this cross-entropy loss, the model learns to reduce the difference between the predicted and true probability distributions. The difference between the predicted distribution and the true distribution is often called KL-Divergence. Reducing cross-entropy loss minimizes this divergence. By minimizing the cross-entropy loss or KL-Divergence, the model learns to align its predictions with the true probability distribution, enabling it to make more accurate predictions. Cross-entropy loss finds applications beyond just classification tasks. It is utilized in various other machine learning scenarios. For example, cross-entropy loss is used to train a language model like ChatGPT. In language modeling, the goal is to predict the next word in a sequence given the context. That is, the model's prediction for the next word is a probability distribution over all words in the model's vocabulary. The true distribution has probability 1 for the correct word and 0 for all other words. By minimizing the cross-entropy loss, the language model learns to generate more accurate and contextually appropriate word predictions.